So before starting today's class, I will announce when we take the when we will take the final exam. Oh no, not how, not when. How we will take the final exam actually. So actually, I did not fix the I do not fix the final exam date yet, but university recommend to take the final exam in the last week because this course is normally provided for sophomore students. So it's a 2학년, yeah, sophomore students. So the final exam will be taken in the last week of this semester. Maybe it's the last week is the December 15th to December 21st, I think, maybe. Yeah, December 15th to from December 15th to December 21st. So that is the last week of this course, this semester. So I believe the final exam will be taken during the last week. Okay, and I decide to take the final exam as online exam, not on-site exam. So because of the severe COVID-19 pandemic, so I think we will not take the final exam as the on-site exam because it's not safe. It's not safe. So we will take the final exam as online exam, and then for this online exam, we will use the lockdown browser, and also we will use Zoom to monitor the students' behavior during the exam. So, and then I will post the detailed instruction about the online exam on the Blackboard. So, but before taking the online exam, you need to prepare for some lockdown browser, and then also you need to prepare the webcam for the Zoom meeting. So yeah, I will post the detailed exam instructions. Okay. Yeah, that is not an easy situation. Then I know actually the online exam is it's not convenient actually. Yeah, I know. It's not easy for me also. But yeah, we don't have any other choices. Okay, and in the previous class, we will learn about the right policies of cash. So I explained about the two right policies, right through and right back. So these right through and right back policies are considered when the cache line is hit for the write request. So write request is caused by store instruction, and then this write request will update the content of cache block because this is write request, not read. So for this write hit case, that means that the requested write data exists in cache memory. So, and then there are two different approaches, write through and write back. So you need to remember how the write through and write back policy works in the cache memory. Also, we can consider the two different approaches for write this case. So there are two different approaches. So allocate on miss and then write around. So allocate on miss means that if the write miss happens in the cache memory, then the requested cache block the requested cache block is allocated to the cache before write. That is, that is allocate on miss. So this behavior of allocate on miss is similar to the miss by read request, right? And then another approach is write around. So the write around means that the requested write block is not allocated to the cache memory because the write is just update the data. So this write request is transferred to the low-level cache or main memory is without fetching the requested block. Okay. Also, we discussed about the performance of cache. So until the chapter 4, so we just assume that the cache event is always hit. So we assume that the load instruction or store instruction only consume one clock, but that is not true because I explained that pipeline processor design. Also, in the single cycle processor design, the data memory and the instruction memory are actually cache. And then I already explained that in the cache memory, there are two different behavior of the cache, hit and miss. So hit case is the same to the what we learned in the chapter 4 actually. So normally for the hit case, the cache memory will consume only one clock. So that means for the hit case, instruction memory and this data memory will take only with less than one clock period. But for the miss case, the requested data or requested cache block should be allocated from the low-level cache or main memory, and then it will take very long time. So actually, for the load instruction or store instruction, may take more than one clock. Also, that is also true for some normal instruction because for the instruction fetch, we need to access instruction cache. So you need to remember that this cache miss events can happen also for the instruction cache. So, and then because of this miss penalty, most of the processor will take more than one clock for more than one clock. That means the CPI of real processor will be bigger than 1. Okay, and then is it because of miss penalty of cache memory? Okay. So actually you need to calculate the actual CPI of this processor considering the miss in the cache memory. So actually for the level 1 cache, there are two different cache memories, like instruction cache and data cache. So we need to consider the miss rate of this instruction cache and data cache. So, and then this miss rate of the instruction cache can be applied for every instruction, but this miss rate of data cache is applied for load and store instructions. That is obvious because this data cache is accessed by only load and store instruction. Okay, so we can calculate the actual CPI like this. So as you can see, the actual CPI is actually it's much larger than the baseline CPI. So baseline CPI means that it's the CPI that is calculated assuming there is no miss event. Okay. So as you can see, the miss rate is just small, very small for in the cache memory. So, but even with this small amount of cache miss rate, the effect, the influences of this miss penalty from cache memory is very high. Is because miss penalty is normally large. Okay. Also, we learned about the average access time, and then this average access time includes the hit time plus miss the penalty multiplied by miss rate. So if we learned about how cache behave for the request toward the cache memory. So you need to also know how the cache works for the request to cache memory. Okay, so first we need to check if the request data exists in the cache memory, and then in order to check this existence of data, then we need to compare the tag, and also we need to check the valid bit of cache line, cache block. Okay, so and then this process is always done for the hit case and then for the miss case, both for hit case and for miss case. So, and then if the hit, then the data is provided to the processor, and then if the miss, then the miss penalty should be added. So average memory access time is the hit time. That is actually the common time for both hit and miss cases, right? Because I explained it is required for tag comparison and checking valid bit, right? So that's actually this hit time is the common time, and then this miss penalty is the additional cycles for miss cases. But we know that the all cache access all requests for cache do not miss. So we need to multiply miss rate to the miss penalty, and then that is the average memory access time. So this average memory access time is the required clock cycles to access data memory or instruction memory. Okay, so that is the example of how to calculate the average access time, AMAT. And I think this is it is not. I think it's not difficult, but you need to know how to calculate this average access time. Okay. And then in the today's class, we will learn about various types of cache memory as cache. And then actually, we assume that the cache is direct mapped cache. So that means that, let's go back to the, here. So it's very slow. So when I explain about the cache, this is the index of the cache, right? And then this index is determined by a certain part of the memory, a certain part of address of data. So actually, this is the address of data, and then we check the some p field of this address, and then we use this p field as the index. So that means this is the memory space, and then but the multiple memory address can be mapped to the same index. So then what's the problem? So for this kind of cache, the multiple memory address can be mapped to the one cache index. So problem is that in the worst case, the load instruction requests some data, but the different load instruction access this data, this data, this data, and this data sequentially. Then what will happen? So even though cache has many other indexes, but only one index is accessed by this load instruction. So other indexes are not used, so it's the wasted, but the load instruction, yeah, right, just access these multiple, actually as a multiple address space. So that means multiple different data, but this multiple different data is allocated to the same space of the cache. So actually the cache is the temporary space in order to reduce the data access latency to the main memory. But if the cache space is wasted, that means even though the multiple data is accessed by multiple load instruction, but this multiple load instruction just access the same index of the cache, then other cache space, other cache indexes are wasted because it is not used. Then that's the problem. So then how can we solve this problem? The straightforward way is map this memory space, memory address to the index 000, and then this to the other cache line, and then this to the other cache line, and this to the other cache line. So that means we can just ignore the index of the cache. Instead, we can allocate the every request to the available cache entries if there are available cache blocks in the cache memory. So that means we just ignore the index field of the address. Then how can we distinguish these different memory address of the different data? We can just store the tag. So if we see that this so this is the direct mapped cache. So for this direct mapped cache, we use this p field, the p field from pin number 11 down to 2 as the index, and then we use the tag for the address field pin number 63 to down to pin number 12. So this tag is used for distinguishing different memory address in the cache. But I said that we can ignore this index. So that means we can use the entire address except the byte offset as the tag. Then we can allocate this every request data to the cache memory if there are available cache blocks. So index is ignored, but we can use the entire field memory address as the tag. So that means the request data can be stored any entry of the cache, but we can also distinguish the different data because we use the entire field as the tag of the data, right? So if we use this type of cache, then we can reduce the wasted cache lines that may be distinguished by the indexes, right? So there is some different configuration of the cache, and then this type of cache is called the fully associative. So for the fully associative cache, then the requested data, the requested block can be stored at any space of the cache, any entry of the cache. Okay. And then we can use some entire field except this block offset as the tag to distinguish the different address stored in the cache entries. But what's the problem? For the direct mapped cache, one index of cache can store the one block, one cache block. So that means if we use some part of address as the index, so if the index is determined, we just compare this one block for tag, right? But for the fully associative cache, there is no index. There is no index, so that means the request data can be any entries of cache. That means in order to check if the request data exists in the cache, then we need to compare tags in every cache line. So that means if the cache memory has 1,000 entries, then we need to compare 1,000 of tags. So the more resources are required. Do you understand? And then so actually, we need, so for the hit case, if we use the cache memory, then we need to reduce this hit cycles, so hit time. So normally we assume that the hit cycle for the cache memory is less than 1. So that means the required access time for hit case is less than 1 clock cycle. So, but if for the fully associative cache, we need to compare the tags in the how many number of entries of the cache. So that means we need to apply every comparator for. So we need to apply the comparator per cache entry. So that means if there are 1,000 entries in the cache, then we need 1,000 comparator. That is also hardware resource. And then it will increase the some area required for this type of cache memory. Also, it will increase the number of transistors required for implementing this cache memory. Okay, so that's why the fully associative cache is expensive, because this fully associative cache requires the more hardware resources. So we first learn about the direct mapped. So direct map means that for the one index, one block is assigned. And then for the fully associative cache, we just so direct mapped. And then fully associative cache, there is no indexes. So that means the cache, the every request can be allocated to the any space of the cache. So, and then this is the very expensive. So we can also think about the some moderate approach between direct mapped and fully associative cache. How? We can assign multiple blocks for one index. For example, we can allocate the 4 cache blocks per index. So that is the moderate approach, like between direct map and fully associative cache, right? In the direct map, only one block can be assigned to the one index. But for the fully associative cache, there is no indexes. So, but we can select the moderate way, that is the multiple blocks per index, like 2 blocks per index, or 3 blocks per index, or 4 blocks per index. And then inside of this index, then if the request block has the same index number, then this block can be assigned to the any space in the index. So, for example, if we use the two-way set associative cache, so set associative cache, that means for the one index, 2 cache block can be assigned. Okay. And then if a certain request can be mapped to this index, then this request can be the data, this cache block can be allocated to the any space assigned to this index. So there are 2 available slots. So for example, for the two-way set associative cache, there are 2 available slots per index. Okay, that is the set associative cache. But if these slots are fully occupied, then the new request, if the new request comes from the low-level cache, then we need to evac the one of these cache block and then update the new request to the one of these slots assigned to the index. Okay. So for the direct mapped cache, then we assign the one cache block per index. So for the direct mapped cache, we use the one comparator. And then this comparator is used for comparing the tag with the address of the load instruction or store instructions, right? And then for a n-way set associative cache, we can allocate the n blocks per index. Then how many comparators are required? There's 1 and right, n comparators. Okay. For the fully associative cache, we need the number of entries, comparators, right? So this is the moderate approach for the cache memory. And then I explained that for the NA set associative cache, n blocks can be stored. So that means for this index space, this cache has the n available slots. So the space allocated to the index is called the set. Okay. And then okay. So set is the group of blocks, and then so NA set associated means that for the one set, so this set is the the space allocated to the index of the cache, and then for the set NA set associative cache, one set can store up to n blocks, cache blocks. Okay. Okay, let's explain. Let's see the example of the associative cache. So this is the direct mapped cache that we learned in the previous class. So, and then in this example, we assume that the cache memory has the 8 blocks, like 8 entries. Okay, so for the direct mapped cache, this is the block number, and then this block number is the actually index, works as the index. Okay, so this is the address of the memory request, and then a certain the field of the address space is used as the index. For this direct mapped cache, the only one cache block is assigned to this one index. Okay, so this is the one block per index. And then let's see the set associative cache. And then this set associative cache shows the two-way set associative cache. Okay, let's say. So for the two-way set associative cache, you need to remember that for the two-way set associative cache, 2 blocks can be assigned to the one set. So this is the set number. Actually, this is the same to the index number of the cache. So set associative cache means that for the one index number, 2 cache blocks can be assigned for the two-way set associative cache. So we assume that there are 8 blocks, but for the two-way set associative cache, one set includes 2 blocks. Okay, so there are 4 sets. Okay, So this is the set, and then for this set, also this set is also occupy the some B field of the address field, but the size of B field will be decreased because there are only 4 sets. Okay, and then for the set same set number, if the address can be assigned to the same set number, then this address space can be assigned to this set. Okay, but there are 2 slots. And how about the fully associative cache? For the fully associative cache, there are no set, there is no index. Okay, so every memory space can be assigned to any slots or any blocks in the fully associative cache. Okay. The fully associative. So actually, for this example, the direct mapped cache is the one way. It's the same to the 1A set associative cache, right? Because this block is the index. The index is actually the set number. So for the direct mapped cache, one set can include the one cache block. The 2A, 2 cache blocks can be assigned to the one set. How about the fully associative cache? It's the 8 way, because there are total 8 blocks in this cache memory. Okay, so if there are n blocks, then fully associated cache is the n-way set associative cache. So this configuration is called the associativity of cache. So this associativity of cache is high for the fully associated cache, and then low for the direct mapped cache, and then NA set associative cache is the some point in the middle of this fully associative cache and then direct mapped cache. Okay. And then let's see how the cache looks like for the different associativity for cache memory. Okay, this is the 1A set associated cache that is direct mapped. So this is the cache index, and then for each index, so tag is stored and data is stored. And then for the 2-way set associated cache, 2 cache blocks can be assigned for the one set. For this is the set number. So for this set number, we can assign 2 cache blocks like tag and data. Okay, this is the 4-way set associative cache. There are 2 sets, and then it's the fully associative cache. And then, as I mentioned, there is the 8-way. Tag is the one set, and then we can store 8 different cache blocks. Okay, if there are 16 cache blocks in the cache memory, then fully associative cache is the equivalent to the 16-way set associative cache. Okay. And then let's see how cache works for the different associativities in the cache memory. Yeah. It's not easy to pronunciate. So associativities, okay, associativities. So in this example, let's compare the behavior of cache for the direct map to a set associative cache and a fully associative cache. And then this is the block access sequence, like 0, 8, 0, 6, 8. So what is the block access sequence? So in the address field, here is the byte offset. So one cache block will include multiple bytes. So this is the byte offset, and then we can assign index and tag. So actually, for the cache block, if we remove this part, then this part becomes the block address. So that is the address for cache block size. Okay. So you need to distinguish this block address and normal address of the computer system. Okay, and then for the computer system, we use the byte address. So that means 1 byte is assigned to the address 1 for the normal computer systems. But for the cache memory, the 1 block size of the cache memory is normally bigger than 1. That means 1 cache block includes the multiple bytes. So that's why we in the address field, the block offset is assigned in the ls of address field. So if we remove this block offset field, because the block size is bigger than 1 byte, then the remaining part becomes the block address. Okay. So this is the block address sequence. So and then let's start from the direct mapped cache. So in this example, the cache includes the 4 blocks. So there are 4 entries in the cache memory, and then that means the index field will occupy how many bits? How many bits? Cache has the 4 block, and then this is the direct mapped. That means 1 block is assigned to 1 index. So how many bits? It's 2 bits. Right, 2 bits. So in order to distinguish these different blocks for the direct mapped cache, and then this direct map for the direct mapped cache, actually 1 index, that means 1 set includes the 1 block. So we need to distinguish the 4 different location of the cache with the index. So index field is the 2 bit. Right. So this is the block address, and then how can you calculate the index? Just divide by actually modulo 4. Why? Because this is the 2 bit. So modulo 4. So cache, this is the cache index. For the block address 0, the cache index 0, 8, 0, equals modulus 4. 0 to 0. So that means this request will be assigned to the index number 0, and then this request will be also assigned to the index 0, 0, and 6. It's 2, 8, 6. So that's the behavior of the cache. This is the first request, and then cache index 0, and then in the initial state, there is no valid data in the cache. That means the cache event is miss because there is no data in the cache. So it's a miss for the 8. So for the block address 8, and this block address is assigned to the cache index 0. But as you can see, in this cache block, this memory address 0 data is already occupied. And then this data is different from the data accessed by block address 8 because the tag is different, right? So the result of event is also is. And then what will happen for this data? This data is evicted from the cache because this cache needs the space for new request for block address 8. So that means, and then there is no available space. No, that means there is no empty space for this index. Do you understand what I say? Okay. So the old data is evicted, and then new data is allocated to the cache index number 0. Block address 0 is requested. Cache index is also 0. So what's the problem? This data is already evicted from the cache. So there's no data for block address 0 in the cache. So the event is also miss. And then what is the old data? Data for block address 8. So this data is also evicted from the cache, right? And then new data, the data for 0 is assigned to the index 0. What's the problem? Same block address is requested, but due to the lack of available space in the cache, because the different memory space is mapped to the same index, and then this index can only store one block. So that's why this cache has no available space for new request like 8. So this is also miss. 6, this request is assigned to the new index. So 6 is occupied to the index number 2. And then still this index number 0 has the data for block address 0. Okay. And then block address 8 is requested, assigned to the index 0 because modulus 4. So what's the problem? In the index 0, there is no data for block address 8. This data is also evicted previously. So event is miss. So for this direct mapped cache, there are 5 misses and 0 hit. Okay. How about the two-way set associative cache? So we assume that this cache has the 4 blocks, And then for the two-way set associative cache, that means two blocks are assigned to one set, the 2 blocks per set. So set number is just the same to the index. And then totally this cache has 2 sets. And that's obvious because there are total 4 blocks in the cache, and then 2 blocks are assigned for one single set. So that means there are 2 sets, right? Elementary mathematics. So this is a set number 0, and then set number 1. There are 2 sets. Then how can we calculate the cache index? So actually the index number is the set number in the cache. So and then there are two sets. So index is the modulo 2 of block address, right? In the previous example, direct mapped cache, there are 4 sets, and then 1 block per set. So we use the modulo 4. For the two-way set associative cache, there are 2 sets. That means 2 indexes. So we use the modulo 2 to calculate the index of the cache. So for this case, 08, 068 are all assigned to the cache index 0 because this is modulo 2. So for this block request for block address 0 is the miss because there is no valid data in the cache initially. 8. This request is also assigned to the index number 0. But what is different? The set number for the set number 0, there are 2 blocks, 2 available blocks. So this data for block address 0 is occupied to this 1 slot, and then this set has 1 available slot. So this new request can be assigned to the available slot here, okay? Here and here, but it's also missed because there is no data in the cache. 0 is a hit because this data is not evicted from the cache because new data is assigned to the new available, is the available space in a set. So this data for block address 0 was not evicted. That this request block exists in the cache memory. Hit 6. Oh, that is also assigned to the index number 0. So what's the problem? For this one set, there are 2 valid blocks. So actually, every block, every slot is already occupied by valid data. So how can we handle this case? It's just simple. In the direct mapped cache, the old data is evicted from the cache if the new data is requested. And it is also true for the set associative cache. Old data is one of old data actually. One of old data is evicted from the cache because it assign the space for new request. But there are 2 old data. Then how can you select the evicted data? So I will explain about the cache replacement policy, but normally if the cache block is least recently accessed, that means that it's the least recently accessed. That means in other words, we evict the oldest data, but it's the least recently accessed. So what is the oldest data? So in this case, this memory 0 block address, the data for block address 0 is recently accessed. That means it's the request by this request. Do you understand what I said? What I said? So there are two valid data in the cache, but this block is recently accessed. So this is the least recently accessed. Okay. So this block is evicted from the cache because this is the recently accessed. So new data for block address 0 is assigned to this slot. Do you understand what I said? Okay. And then for 8, this data is evicted from the cache, was evicted from the cache. So this is the miss. But for this case, this set number 0 has the two valid data. Then what is the least recently accessed data? This one. Because this is the oldest accessed data. So this new request data is assigned to this slot, and then this data is evicted from the cache. Do you understand? So for this two-way set associative cache is the 4 misses and 1 hit. So there is 1 hit. So it's better than direct map cache, right? How about the fully associative cache? For the fully associative cache, there is no indexes. So index is not considered in the fully associative cache. So if there are available slot in the cache, then this new request is stored in the available slot, any available slots in the cache. So no indexes. So 08068. So for this block address 0 is occupied the any slot actually. So here it's a miss. And then for the 8, for the request for block address 8 is assigned to the new slot. Oh, it's okay, miss. 6, for the request for block address 0, this cache has already this block, is memory 0. So hit is found in the cache. 6, no index. So 6, this block can be assigned to any available slot. Here. 8, compared to the tag here, so it's a hit. Then how about the fully associative cache? 3 misses and 2 hit. So I hope that you can understand how cache behave differently with the different set associativity. Okay. So this is the direct mapped cache, set associative cache, and then fully associative cache. So performance, and then also we can compare the cost. How about the performance? So if the hit rate is high, then we can say that the performance of a certain cache is also high. So we just compare the very simple cases, but if we compare this simple example, then we can know that fully associative cache has the highest performance, right? Because the hit rate is highest for the fully associative cache. So performance high, it's low, and this is moderate. How about the cost? Cost is also high because fully associative cache requires many comparators, right? Low and medium. So the expensive thing is shows the higher. The more expensive cache configuration exhibit higher performance. And that is also true for this engineering world, engineering space. Actually, if we invest more resources or more cost, then we expect that the performance will be higher. But that is also true. But we need to select the optimal point for the cost and performance of the cache. So this is the set associativity, and then this is the performance. The y-axis is the performance, and the x-axis is the set associativity. Then if the performance increases like this, then we will select the higher set associativities, right? But in reality, the performance of a cache looks like this for the various set associativities. So that means the performance increase steeply first, but the performance is saturated. So increased associativity decreases mislead but diminishing returns. So that means performance is saturated by set associativity, higher set associativities. Okay. So this is the data cache, and then this is the result of the mislead. But when we learn the spec 2000 benchmarks, and then as you can see, this is the mislead. So 10.3% for the 1A set associative cache. This is the direct mapped cache. For the 2A, 8.6, 4A, 8.3, 8.1. So as you can see, the performance of a cache is saturated by higher set associativities, right? Okay. And then let's see how the set associative cache is organized. So for the set associative cache, like this is the example of four-way set associative cache. That means there are 4 cache blocks per set. So that means 4 blocks are assigned to on a single index number. Okay. So this is the address field. And then this is the example of 32-bit address field. And then what is the block size? What is the one block size? What is the one block size? 4 byte. Is it because 2 bits are assigned for block offset? Okay. So 2 bits assigned for the block. So that means one block size is 2 to 2 equal 4, right? So one cache block size is 4 byte, and then so this is the 4-way set associative cache. That means 4 blocks can be assigned to one set. And then there are 256 indexes here. And how many blocks exist in the cache? 256 indexes multiplied by 4 equal 1024 blocks per cache. Okay. So this 8-bit becomes the index field, and then additional bit, remaining bit, like 22 bits, becomes the tag. 22 bits become tag of this cache. Okay. So this is the index. So, and then this is the 4-way set associative cache. That means 4 different cache blocks can be assigned to the one index. So in this case, when the request is given to the cache memory, then we need to compare the 4 different tags, because in one index there are 4 different cache blocks, right? So obviously we need to compare 4 different tags. Understand? So this is tag, and then the cache is accessed by index number here, and then this one index includes the 4 blocks. So when the cache index is accessed, then cache generate the output this valid bit and tag. So this is the valid bit and tag. So this tag, stored tag, is compared to the tag of the request. So here. So you can find 4 comparators here, right? And then also we need to check the valid bit of the cache block. So this is the valid bit. Okay, and then if the one of cache blocks in a certain set is hit, that means one of this line becomes the 1. So this is the OR gate. That means if the one of this line becomes the 1, then this is the hit. Okay. And then if the hit, then we need to also select the valid cache block from the 4 available cache blocks in a single set. So we need the multiplexer here. And then this multiplexer select the hit cache block from the selected set index. Okay. So this is the organization of the set associative cache, and then you can compare this organization with the this figure. This is the direct mapped cache, and then you can find the difference between direct mapped cache and four-way set associative cache, right? So this set associative cache is also important. Okay, it's important. Okay, and then I will explain about the replacement policy. So when I mentioned the two-way set associative cache and then fully associative cache, then actually for this example, two-way set associative cache, you can find the situation that we need to select the which cache block will be evicted. So if there are no available slots because in a single set every block has the valid data, and then new request is sent to this cache memory, then we need to select which block will be evicted from the cache because there are two available slots. That is also true for the fully associative cache because this fully associative cache is also kind of multi-set associative cache because this is also four-way set associative cache. So way of the fully associative cache is the same to the number of cache blocks. Okay. So we need to set the replacement policy. So replacement policy means that if there is no available slot in a set and then new request comes, then we need to evict the one data from multiple valid cache blocks because we need to assign the new one available cache block for the new request. Right. So this is the code. This policy is called the replacement policy. So cache replacement policy. Direct map, no choice because for the direct map cache is the one block per index. So for the one index, only one block is assigned. So we don't have any choice. So if the new request comes, then the old data should be evicted from the cache. But for the set associated cache, we have n blocks per index for the n-way set associative cache. So for this case, we need to select from the n valid cache blocks. Okay. So if there are available blocks in a set, in an index, then we can allocate the new data to the one empty block. That is obvious. But if the all blocks are valid, we need to select the one block from the all available all valid old blocks in a set. So the most reasonable policy is the least recently used, and then this policy is called the LRU. So least recently used. So I already explained about this LRU policy in the previous example. So if you see the name of this policy LRU, then you can figure out how this LRU policy works in the cache system. Least recently used block is selected for eviction. Okay. So this is the least recently used policy, but this can be complex for the high set associativities. So that means this LRU policy is simple for the two-way set associative cache, but it's manageable for four-way, but too complex for the 8-way or 16-way. So if the set associativity is high, then LRU policy will be very complicated. It's very complex for implementing as hardware. So sometimes we use the random. So randomly select the blocks to be evicted from the valid cache blocks. So we can sometimes use the random replacement policy. But as you can see, the performance of this random replacement policy may be similar to the LRU policy for the high set associativities. Okay. So I think we need to stop here, and then for the next class, we will learn about the multi-level cache. But for the today's class, you need to remember, you need to know about the various set associativities in the cache. Okay. Okay. Do you have any questions? Okay, thank you for listening, and then see you in the next class. Thank you.